Hello everyone, my name is Tingwei Zhang. I'm from Cornell Tech. Today I'm going to present our work on adversarial illusions in multi-modal embedding. And this is a joint work with my collaborators, Rishi, Eugene, and my advisor, Vitaly. Multi-modal models are now everywhere. There are multi-modal chatbots, image generation models, and video generation models are on their way. These models are all based on multi-modal embeddings, and many big companies like Google, Meta, Amazon, they all release their own embedding models to support those tasks. The purpose of these embeddings is to create a single, uniform representation that captures the meaning of the input regardless of whether it's a text, an image, a video, or an audio. Okay? As you may all know, the word embeddings came out around 10 years ago. The magic of word embedding is that they take words that are similar and convert them into parallel vectors. Multi-modal embeddings does the same thing, except for that they expand the input modalities from text to other modalities like image, audio, and video. The key concept of embedding is alignment. The alignment makes sure all the semantically similar input are close to each other in the embedding space, so that the same embedding can be used to supporting different downstream tasks. In this example, the embedding of the wolf's image and the embedding of the text wolves lie close to each other in the embedding space because they are semantically related. We define this alignment between the embedding of the semantically related inputs as organic alignment. With the aligned embedding, you can take the vector and just throw it into different downstream task models, and you can get amazing results like a generated image, a classification result, and some generated text. In our work, we observed that the organic alignment in multi-modal embedding is actually very vulnerable. By applying a small perturbation to an input, we can change its meaning and make it align with any target in any modalities. Here's an example. We apply an unnoticeable perturbation to a wolf's image. Now it still looks like a wolf's, but now it's aligned with the text sheep in the embedding space. In this formula, theta m denotes the encoder for the input modality, theta m bar denotes the encoder for the target modality. By adding the perturbation delta to a clean input x, we managed to get the multi-modal adversarial illusions whose embedding is aligned with the embedding of the target, yt. And we call this alignment as adversarial alignment. Here's an example. We have an audio of a wolf howling. If we take the audio and try to generate an image or text description from it, they all talk about wolves or dogs. Now we align it with a picture of a sheep. Everything generated from it now talks about sheep instead of wolves or dogs. Note that even the text generation at the last column is also compromised, but text modality is not even one of the input modalities. Although this might look like adversarial examples, but they really aren't, because they target alignment, embedding alignment, and they are task agnostic, which means the adversary does not need to know the task when he attacks the embedding, and these attacks are cross-modal. What's more, the adversarial alignment is hard to defend with traditional defenses because you can always make the target close, align the input close to the target in the embedding space. To summarize, our adversarial illusions align any input with any target and compromise all the downstream tasks. Let's see another example here. That's Sam Bankman-Fried. You've all heard of him. Let's perturb this image and put this nice gentleman in jail. And it works. This example illustrates how alignment captures meanings or semantics. We align the audio of a dog barking with the text, a classical concert. As the audio becomes more aligned to the target, you can see the generated image becomes more close to a classical concert. This means the entire meaning of the input is captured in the alignment. If you change the alignment, you change what the input means to the downstream models. Okay? This figure shows some potential threats of our attack to real-world applications. Our illusion successfully makes the text generation model to describe a normal thermal image as an image of someone doing illegal activities. In our work, we discussed different threat models in our work. We discussed white box setting, which gives the attacker full access to the target model. We also discussed a bunch of black box setting, including transfer setting, query-based setting, and hybrid setting. We also proposed different attack techniques for each of the threat models. We have a white box attack based on projected gradient descent. We have a transfer attack by generating local illusions with surrogate models. We have a query-based attack based on a variation of a square attack. And we have a hybrid attack by combining both transfer attack and query-based attack. And it seems to be very effective in practice. Please read our paper if you are interested in the technical details. Empirically, our attacks works very well. Success rate somehow varies depending on the downstream tasks. But the fact that some numbers are a little bit lower than 100%, in many cases, it's not because our attacks are not good. It's because the downstream models are not that good. And in general, these attacks all reach pretty good results and seem to be very successful in a task-agnostic way. We also got pretty good result with the transfer attack. It shows that the illusions works for one embedding, might transfer to another embedding as well. It's also worth to mention that we tried our black box attack on Amazon's Titan embedding. It is a closed-sourced, commercial, proprietary embedding, which Amazon charges people for using it. And we got pretty good result against this model, especially with our target technique, with our hybrid techniques. We also discussed a bunch of defenses in our paper, and all of them are hypothetical. No embeddings is actually using any defenses. And I'll just say a few words about certified defenses for the sake of time. And certified defenses is a strong defense come from a traditional adversarial robustness. It suggests that if two images are within a small distance to each other, they should be aligned. Here are two images. These are within the same distance to the original clean image. And one of them should be aligned with a clean image, and the other should not be aligned with a clean image. So therefore, you cannot determine which one should be aligned with a clean image by just looking at the distance. This means the certified defense cannot be directly applied to the multi-modal embedding setting, as it will either make the embedding too robust to be invariant or not robust enough. So the point here is we don't even know where the trade-off is between the robustness and the invariance in a multi-modal embedding setting. And even if you have these very strong hypothetical defenses, it's not even clear how to adapt it into a multi-modal embedding setting in a task-agnostic way. To summarize, multi-modal embeddings are very vulnerable, and our attacks are task-agnostic, which means adversary does not need to know the task when he attacks the embedding. And at the end of my presentation, I want to invite you all to think about this question, about what did we all learn from 10 years of research and numerous papers published on adversarial robustness. After all this research, why do major company players still putting out commercial models that are highly vulnerable, and it's not even clear if they can ever be made robust? Okay, our code is available on GitHub. You can scan this QR code to take a look. And thanks to the committee for the Distinguished Paper Award. And thanks to my collaborators. And thanks for the support from my family and friends. Last but not least, we have special thanks to the famous painter René Magritte, whose painting inspired our work. Thank you for listening.